We're going to learn about work and doing work in physics, which is slightly different from what you have already heard in your everyday life. So, the idea of work came from a scientist, Gustav, who was studying the engineering process of raising water from a underground mine. He realized that the energy that was being transferred from the steam engines were pumping the water vertically out from the ground. So then he described or defined work as the transfer of energy. So if we have to put this in words, we're going to write down the definition of work as transfer of energy. So just wanted to give you the background of where it comes from, but we also know that energy is either added or removed from the system. Just like in the water case, steam engines were adding some energy and then the work was being done by raising the water to the ground. If mathematically we define work, it is defined with the product of force and the displacement. Now, if you remember, force and displacement are the terms that we've already seen before. So these are the old terms that we have already known. And work relates both force and displacement. So if we want to write down the equation, it's either defined as the product of force and the component of the displacement parallel to the force, or we can also define it as, we'll talk in detail about these two where it comes brings us back to the idea of vectors, vector components. So we'll check these ideas later, and when I write down the equation I'll explain it again how to help you understand. So let's talk about the work. The symbol we use is capital W. The unit is same as energy and it's joules. Capital J is the symbol we use for the units, and keep in mind it's same as energy because it's the transfer of energy, so they both are going to have the same units. And if we define it as a quantity, we say that it's a scalar quantity, which means that we do not need the direction, we only need the magnitude in this case. Let's take a look at an example. Let's say we have a block that already has energy at the start. Let's say it has 5 joules of energy at the start. And then you're going to do some work somehow on the block, and let's say we have done some work in the let's put some numbers for the work done on the block, and let's say we have done about 3 joules of work on the block, and the question is going to be phrased as asking us how much energy does the block have in the end after the work is being done. So in this case, or in this scenario, how to answer these type of problems, we first need to understand what does the 3 joules of work mean. So the 3 joules of work that we have done on the block can be useful in a sense that it can make the object move from its place or give some kinetic energy or change its location or position. So that's also another type of work that can be done on this block. So let's find out the energy that the block is going to have after the work has been done. So we add the start and the end energy, and we get a total energy of 8 joules. And if you notice, the block now has more energy. This time we have a block that has 10 joules of, let's say, kinetic energy, and it has 0 joules of gravitational potential energy. So what it means is that the total energy, or the whole energy that this block or this object has, is 10 joules, and it's all kinetic energy. Now let's say we have done some -6 joules of work on the block. What this -6 joules is going to help you understand is how much energy has been transferred to the block. The question can be phrased again as how much energy does the block have in the end. So let's start by understanding the -6 joule means that some energy has been removed from the block, and keep in mind it's not telling you about the direction, left or right. It's only telling you whether the energy has been removed or added to the system. Now work is a scalar quantity, and that's why negative sign is not going to tell you the direction. It's only telling you about the energy transferred in and out of the object. So let's calculate the energy now for the block. We'll just do the same thing. We'll add the start beginning energy and ending energy and find the total energy. The beginning energy, as I said before, it's 10 joules all kinetic energy plus the negative 6 joules, and we get a total of 4 joules of energy. Now, if we assume all of the kinetic energy left, um, since it started off with all kinetic energy, then it means that its energy has actually decreased. If you think of it, that what is kinetic energy? Kinetic energy is actually related to the energy because of motion. So if an object is moving and has some kinetic energy and now has less kinetic energy, what it's telling you is that the motion has actually slowed down. So negative energy or negative work means that the object lost some energy by slowing down. That's one way to understand the negative or less kinetic energy of an object. Now let's write down the equation to calculate work in physics. So I'll write down the equation, which is a product of force and displacement and also cosine of the angle. Now F we already know is the force on the object. S we already know as displacement or how far the object has moved. The cosine angle theta is the angle between the force and the displacement. So this is where we will understand the components that I was talking about. If the force component is in the direction of the displacement, then it is going to have some work done. And we'll see these, get a better understanding in the examples. W is the work done on the object. Now if we write down the units for each of these quantities, work is always going to be measured in joules, and force is measured in newtons, displacement in meters. Now we get another unit for joules, which is a product of newtons and meters. Now let's do some examples to help us understand the work done in physics. So let's say we have a crate on the ground and we have it tied to a rope and we're pulling it with the rope, so there's a tension force on it and it's going to move on the ground. Our displacement is along parallel to the ground, but the force has an angle between the displacement. So how much work is done on this crate? If you have to figure this work done on this crate, we need to have some numbers. Let's say we have the angle of 30 degrees, displacement is 2 meters, and the applied force or the tension force we're applying is 50 newtons. We can start up with the equation again. Write down the equation, plug in the numbers for the force and the displacement. Keep in mind we're not going to plug in any directions because the angle part is going to take care of the direction between the force and displacement. So when we plug in the value of the angle 30 degrees, that's already taking care of the direction or the angle between force and displacement. So when we do the calculations, our answer comes out to be 86.6 joules. Now this is the work done on the crate by the force as it moves. Let's take a look at another example. Let's say we have the same crate. We have it tied to the rope again, and we are applying or pulling the rope with some force, and the crate is moving in the same direction as the force is being applied. Now, how much work is done on in this scenario on the crate by the force that we are applying parallel to the displacement? Let's use the same numbers for the force. Let's say we have a tension force of 50 newtons and displacement of 2 meters. Same numbers, but we have to figure out the angle between the force and the displacement. Now that's going to be tricky because if you draw the arrows, you can clearly see the angle between the two. Force and displacement is they're parallel and it has to be equal to 0 degrees. So let's write down all the numbers. We have force, displacement, and the angle, which is, since they're both parallel, we're going to take theta as 0 degrees. Now when we plug in all the numbers in the equation, again we're not plugging in the directions because the angle took care of it. We got a work done of 100 joules. Now we apply the same force over the same displacement, but this time in a different direction, or the angle was different. And if you notice, the answers that we're getting is that this time in example 2, we did actually more work on the crate, or more useful work was done on the crate. So let's take a look at another example. This time we're going to change the angle but keep the force and displacement the same. Let's say we have the same crate, pulled with a rope. This time we have a different angle, and we're trying to find out how much work is done on the crate. We think that somehow the crate has moved to another position, and that's what I've placed as a dotted box. So the angle, if you look at the picture, it's 180 degrees here, and we're going to use the same force applied and the displacement from the previous examples. This time we have a different angle, which is 180 degrees, because they're in the opposite directions. Now when you plug in all these numbers, you know cosine of 180 is -1, so we are getting a negative answer this time. Now if you try to understand, this is basically the transfer of energy away from the crate. That's how much work we have done on the crate. Let's compare our answers to example 2 and 3 this time. Now the work done in example 2 was 100 joules, but in example 3 we got a -100 joules. What it means is that example 2 we were adding more energy or doing positive work, whereas negative answer was telling us removing energy and doing negative work. So our last example, this time we have a special scenario where we have the same crate, but this time we are applying a force in the upward direction, and let's say the crate is going to move somehow on the ground in the parallel to the ground. Now this time the angle is 90 degrees. If you have to find out how much work is done on the crate by the force, we'll plug in the numbers that we know from the previous examples as well, but this time angle is 90 degrees. You also know that cosine of 90 is equal to 0, which means that we're getting a work of 0 joules. What it's doing is that we are applying the force, but it's not helping or harming the motion, and it's not doing any useful work on the crate. The force is not adding or removing energy, which means that there's no useful work done on the crate, or we're getting 0 joules of work. So practically, you might be saying that you're doing some work, but in physics, it's no work.